Restart the next video. Because this is kind of a, there's like a major shift going on here between 2.5 and 2.6. So map 35, section 2.6 is on basic graphs. If I could ever find the start of my notes for it. I just do this. There we go. So one thing that one vocabulary term they want me to use to show you, and it is important for your long-term understanding, the word continuity. Continuity. When we say when continuity is a function has continuity or is continuous, or is continuous on a domain. Maybe let's just say over an interval on the domain. If it's hand-drawn graph, never has the pin move the page. This hand-drawn graph can be sketched or drawn without lifting the pencil. All right, pin. Continuous could be a mouthful. Same with continuity. Continuous is phonetically. Continuous. So non-continuous graphs have a hole, basically. Or gap. I'll draw a couple. Give you an idea. One thing I could do is I could have a graph that goes like this. If I do this right, if I lined them up right, it's called the greatest integer function. It's dumb. It's in the notes to teach you, but I'm not teaching it. It's a fucking dumb function and no one's ever using it. That's really discontinuous. That's a better word, discontinuous. I fucking brain farted earlier. Non-continuous is not a fucking word, discontinuous. The word. It doesn't have to have a whole bunch of holes like that, though. It could simply be a straight line that has a gap in it. The red line has it is the same. These are both discontinuous graphs. Some that are really noticeable, this is, and we're gonna cover this one later. This is the graph of y equals 1 over x. I can't draw that pin without lifting it from the paper. Now, we leave the hole, we have the hole like this, so I could technically draw this line here with the hole there without lifting my pin from the paper. But the idea is if I don't put the circle where the hole is to emphasize it, the pin literally has to be lifted up and continue. We draw the circle to make sure that you can see it, that there's a gap there. And so they might ask you where these intervals are continuous. I'm not going to look at the blue line, I'm going to look at the red line. Let's say this is at x equals 2. It is continuous on negative infinity to 2. And 2 to infinity. And they might ask you to use the union sign in between. So that's the domain. The domain here has the same setup, but it's discontinuous at x equals 0. So here I could say negative infinity to 0 in union with 0 to infinity. All right, kind of boring. Has everyone got what they want out of that? If you need that longer, say so. Otherwise, I'm turning the page.
Sorry, since since I see blurry, you can tell me just what is under domain. I don't.
It's
understand
negative infinity. Oh, right here. It says discontinuous at x equals 0.
This was x equals 0.
Yeah.
Oh, okay, negative infinity. And next to negative infinity, that's comma, negative infinity, and what
Comma
is
0.
Comma 0. U 0 and infinity, right? Okay.
Yeah.
Thank you.
So the idea here for the following graphs, we're going to do the basic shapes, basic graphs for 2.6. We're going to do a bunch. And in 2.7, we learn how to move the basic graphs all over the page, how to shift them. But the ideas for the basic graphs translate to the shifted graphs just as well. So if you learn the basic graphs, you kind of can't go wrong later on. So the first basic graph is called the identity graph. f of x equals x. Whatever x equals, y equals. -2, -1, 0, 1, and 2 is going to get me the same values on the y side. This makes a diagonal line. And it's perfectly diagonal. So a couple things to note about it. X or the function is increasing on its entire domain. Or increasing everywhere. It's continuous everywhere. And both its domain and range are negative infinity to infinity. If you don't remember the values on the right, just plug them into the equation. If I take x equals -2 and I plug it into y equals x, I get y equals -2. If I take x equals 0 and I plug it into the equation, I get y equals 0. That's going to hold true on the next equations too. On all of these, you can do this. The next one is the squaring function. F of x equals x squared. Let's just stick in the same -2, -1, 0, 1, and 2 and see what happens. On each of these, I want to square it. If I square -2, I get +4. If I square -1, I get +1. Squaring 0 is 0. And I get, for squaring 1 and 2, I get the same values as -1 and -2 because the squaring just got rid of the negative sign. If I start plotting these points, I get something like this. And if I connect them, I gotta make some kind of curve. So this is the graph of y equals x squared. So we can see that from the graph, it's decreasing. From negative infinity all the way up to 0. But not at 0, it's not decreasing at 0, it's not increasing at 0 either, but it is increasing everywhere after 0. We can see it's continuous everywhere. The domain is all real numbers. The range is restricted though. It goes from 0, including 0, up to infinity. We will do a little bit more. It's not mentioned in 2.6, but I think it's worth noting. This point where the decreasing and increasing stops, that point is called the vertex. I kind of like to think of it as like the center of the graph. And then you go outward. If you start at the vertex, starting at vertex, if you go left or right 1, you go up 1. And if you go left or right 2, you go up 4. So left 1, up 1, right 1, up 1, left 2, up 4, right 2, up 4. And that's going to be true even when we do 2.7 and we start moving the graph around. That kind of 1, 1, 2, 4 follows through. Any questions on the squaring function? Are we having fun yet? Awesome. How you guys doing online?
It's a little bit blurry, but I can understand what you're doing.
When it's over, Josue, you might restart your computer and like any section you're having trouble with, see if watching it again fixes it, because everyone else says it's not blurry. So it's on your computer. Whatever's causing it is your computer.
Yeah, that's mine. Yeah. But I can see what you're doing. Just when you like do it a little bit, like when the letters are smaller or the numbers, I can notice, but most of them I can notice what they are.
Okay, I'm trying to zoom it in a little bit to help you. All right, let's look at the next basic graph, which is the cubing function. F of x equals x cubed. If I cube -2, I get -8. So -2, -8 is a point. I cube -1, I get -1. So -1, -1 is the point. Cubing 0 is 0. And the 1 and the 2, the cubing part stays the same, we get the same values, and we keep the same signs. 1 cubed is 1, 2 cubed is 8. So I get 1 comma 8 and or 1 comma 1, sorry, and 2 comma 8. I got all hasty. Graphing this one is a little less fun. It doesn't require a very wide graph, but it does require a tall graph. Again, I'm going to treat this as my center idea and work outwards from there. So if I go left, I've got to go -1, -1, left 1, down 1. And if I go to -2, -8, I go left 2, down 8. I go to the right, I gotta go right 1 and then up 1. That'll get me to 1, 1. And I go right 2 and up to 8 to get me to 2, 8. That's not very curvy looking. God, that looks like shit. So we can see it's continuous everywhere. I didn't have to lift my pen. It's also increasing everywhere. Both the domain and the range are all real numbers. Which you can write as that, or you can write as -infinity to infinity. And it kind of has the same idea with like the last one where I said left or right 1, move up 1, but it's kind of like whatever you move, do the same thing in the same direction you're going. So if I go right 1, I go up 1. If I go left 1, I go down 1. That should be a 1 right there. If I go right 2, I go up 8. If I go left 2, I go down 8. From the center. And these values are the cubes of the numbers on the left. So these are the cubes of that. If I wanted to see how far up and down I go with left 3 or right 3, I just need to cube the number because we're doing the cubic function. 3 cubed is 27. It should be down. I'm off screen because I zoomed in too much. Having fun? How many more we got? We've got square root, cube root. Absolute value and piecewise. Oh, and sideways square. These fucking gloves. It's the wool in the gloves is doing it. I get ink all over my fucking hands when I do this. And so I'm gonna get gloves so that I'm not.
I thought it was because you're cold. I was like, why is he wearing polo gloves?
No, it's because I get, like, when I get home, after like on Tuesdays and Thursdays, I have a class for 5 hours in a row. I come home, my hands are all fucking inked up. So this way, like, generally, maybe my fingertips a little bit, but like, only my thumb has it right now. Other than that, all the ink's on the gloves. Yeah, use the brain. All right, let's look at the other functions. Let's look at the square root function. F of x equals the square root of x. What happens if I try to take the square root of -2? That shit's a bust. I'm gonna get a complex number. I don't like it. Doesn't show up on the real number line. Same thing with -1. It's out also. So if we want 5 numbers, maybe we'll pick a. In fact, using -2 and -1 suck. And using 0, 1, and 2, 0 and 1 are fine, but if I want to take the square root of a number and I want to draw it on the graph, square root of 2 is hard to draw on the graph, right? You got a decimal, it's like 1.3 something. So like, let's pick square numbers for the x. And if I want 5, maybe I'll just pick the first 5 square numbers. So the square root of each of these numbers is my first 5 integers. And if I start plotting them, that's all you can really do. 0, 0, 1, 1, 4, 2, 9, and 3. 16 is way over here, and it's up to 4. That is the graph of y equals square root of x. Yeah.
So is it just, well, I'm assuming so, but is it just impossible to graph imaginary?
On a real number line, no. Later on, if you, I don't know that you ever do it here at CUS, but if you go far enough in mathematics, you can The way you end up graphing complex numbers is you treat the x-axis as the real axis and the y-axis as your imaginary axis. You start plotting points that way. So, but like it doesn't, the complex numbers, we don't have, like, they're not something we can use in everyday real life. I mean, the complex numbers show up in the equations for electricity, alternating current, and stuff like that, but not a lot. So in general, to answer your question, no, most of the times, no, you're not graphing the imaginary numbers. All right, so where is this increasing? This is increasing on its whole domain. But the domain starts at 0 and goes to infinity. And that's actually going to be our range too. That'll be a range also. It is continuous on its domain 0 to infinity. Which is its entire domain, continuous on its entire domain. Rather than jumping to the cube root one, I am going to show you the x equals y squared because it builds right off this motherfucker. Or y squared equals x. If you take the square root of both sides here, we get y equals plus or minus the square root of x. So I'll just do the first 4 points. It has the same thing as y equals square root of x. 1, 1, 4, 2, 9, 3. Because this is y equals square root of x. And then y equals negative square root of x goes along the bottom. So we do the same thing, but our outputs are negative here. So when we go right 1, we're going to go down 1. When we go right 4, we're going to go down 2. When we go right 9, we're going to go down 3. So maybe I'll put a little vertical or a horizontal line here to separate that graph from the other one. All the information we had above, for the most part, stays the same. Except we don't say it's not increasing or decreasing, because it does both. So we don't talk about increasing or decreasing. We can't even write this as a function. This is not a function. Why is that not a function? It doesn't pass the vertical line test. God, that blue line I drew is shitty. the domain is the same as y equals square root of x, it's still, the domain is still 0 to infinity. But the range is now all real numbers. And that is the x equals y squared graph. If you rotate it sideways, it looks like the y equals x squared graph. It looks like a parabola opening to the right. So this one, let's write that down. That's worth noting. It's a parabola that opens right. In fact, so much so, when we did the parabola, we said we go left to right 1, we go up 1. We go left to right 2, we go up 4. If I do that here, rotate it sideways, I go left to right 1, I go that way 1, up 1 in that direction. Left to right 2, I go up 4. So it still has the it's just like taking the parabola and doing it sideways. So that's kind of neat. If you're a geek like me. You guys ready for the cubic function or cube root function? So enthusiastic. This is some good shit. F of x equals the cube root of x. So we want to do the same table that we've been doing before, but we want to plug in values that have good cube roots. So we're going to pick values that are cubes and see if we can do it. That should look like an 8. It looks like 2 zeros. When I take the cube root of -8, oops, that's not there. -8 goes in here. I get -2. So we can do the cube roots of the negative numbers here. And you're going to find it's just like doing the cube function, but in the backwards order. Kind of spaces out a little bit more than I meant to. I'll still do my centers and the zeros. And it's kind of like the cube root one, except the Y's and X's are switched. Instead of going right one, up one, I'm gonna go up one, right one. And up two, right eight. And on the bottom side, if I go down one, I'm gonna go left one, and if I go down eight. Or down two, I'm gonna go left eight. There we go. That's what I meant to say. So. Same old song. What's my domain and range here? It's all real numbers for both, right? Negative infinity to infinity. What regions is it increasing and decreasing on? It's definitely increasing from 0 to infinity. Because as we go right, we're going up, right? As I go right, we're going up. It's a little hard to see. Over here, as I do it too, as I go right, this is going up a little bit too. If I started here, I can see that if I made a little line, as I go right, I'm going up still. So it's actually increasing everywhere. The tricky one, I agree. Which means if it's increasing everywhere, it's decreasing nowhere. Continuous everywhere though. Most of the things we're doing right now are continuous everywhere. Ready for more? The last one we're really looking at is the absolute value function, then we're going to talk about piecewise functions. Need to get some non-wool ones for as it gets hotter. This is gonna be a fucking miserable come fucking May.
Like latex to get all stiff.
Right. It'd be colorful gloves though by the time I was done. Ink all over them motherfuckers. This is actually a function too. It will pass the vertical line test. And no matter what I stick in, I get the positive version of it. Which means I have no negative values for y. I put my center there. As I go left or right one, plus or minus 1, we're gonna go up one. Left one, up one, right one, up one. And as I go left or right two, I go up two. Makes a V. In fact, it's actually a right angle. If you look, if you did it like made a triangle thing, it actually makes a right angle. This line right here is the y equals x line. This line right here is the y equals negative x line. We can see it's continuous everywhere. It's decreasing from negative infinity to 0. And increasing from 0 to infinity. The domain is all real numbers. And the range is only positive numbers or non-negative. We can include 0. I think I've showed you guys this before, but another way to write f of x equals the absolute value of x is I can say it equals x if x is greater than or equal to 0, and it equals negative x if x is less than 0. I don't know if the screen for Zoom users. This is what we call a piecewise function. The behavior is different for different parts of the domain. Intervals on the domain. Let's look at doing another one, because I want to show you how to graph them when you have some ones that are not so, like, absolute value makes a nice little V, it's easy to remember. Let's look at one more piecewise function, just like how do I graph piecewise functions? Okay, it's clear that shit changes here at x equals 1. I'm getting that from here. So what I want to do is I'm going to graph the part that has the equal one first. I mean, it doesn't matter how you do it when you're comfortable graphing them, but I think when you're learning it, it's pretty helpful. So for this one, the part where it's equal, I've got, if I say this is y, I've got y equals 4 minus x, or y equals negative x plus 4. One way of doing this is to graph that whole line, but do it like very, very light dashed line. So if I do this as a very light dashed line, I have an intercept at 4. And the slope says I'm going down 1 over 1 as I go. So I kind of have something like this as I go down to the right. And it would go up the other direction. Now I go, okay, where is my graph start? For values of x that are greater than or equal to 1, which is x is 1 is right here. I'm going to go there and I'm going to put a point on the graph right on that line and draw the line in the direction that it says. X greater than 1 is this direction. So that gives me my y equals negative x plus 4. I can do the same thing for the other one. I can make a dotted line for the y equals 2x plus 4. It also has a y-intercept of 4. And as I go down 2, I go left 1. Or as I go up 2, I go right 1. Maybe I should have made my y-axis a little bit longer. I don't have an equal sign here for the x where x is near 1. So where x is 1 on my y equals 2x plus 4 line, I'm going to put a circle, a hollow circle. Hollow because x is less than 1. And this line is only good for values that are x is less than 1, which is this direction. If we look at the domain, we can look at the domain in the range. It's definitely not continuous, right? The absolute value graph was continuous. This one is not continuous. So piecewise functions, it's hit or miss whether it's continuous or not. You kind of have to graph it and see what happens. What's my domain here? In my range. It's all real numbers for the domain, right? I can pick it, put in an EX value. I can even put in X equals 1. It's on this line here, not that line. But the domain is all real numbers. What about the range? That's a little tricky. It's going up to here, it's stopping right here, right? I can go start at negative infinity and go up to there. Where is that going up to though? Negative infinity up to what? Well, it's on that line and it's where X equals 1. I can use that to my advantage. I can stick in X equals 1 right here and see what Y value I get. I'm going to get 6. So that is going up to where Y equals 6, but it is a hollow circle there. It doesn't actually hit the 6. So instead of having a bracket, we will have parentheses, but it only goes up to 6. And where is it increasing and where is it decreasing? Remember, both of these are from, as you go from left to right, is the graph going up or down? So that's what you said, but the only thing we got to make sure is we do the brackets right. The increasing, it doesn't actually include the one, so we're going to put parentheses here for increasing. Decreasing, it's kind of iffy if you want to say it's decreasing at 1. Depending on who you talk to, they're going to use a parentheses or a bracket. I'll have to look up to see what they say in this book. I'm going to guess they say the parentheses, because as I pass over the point from negative or the negative side of 1 to the positive side of 1, it changes, so it's not kind of either. They're not going to include the 1 anywhere. And that'll be it for today's lecture.